Welcome back to the course on geometry and arithmetic of curves of low genus. Today, we are going to speak about Riemann Roch spaces. Okay, so remember that for a curve, which is always now going to be a smooth, projective, absolutely irreducible curve over field K, we had introduced the function field of K. And this is a K bar vector space, of course, but of infinite dimension. So we would like to cut pieces of it that would be of finite dimensions. That would be much easier to handle, right? So the definition is the following. We take a divisor, so let D be a divisor on C. And we are going to denote L of D, the function f, so inside K bar of C, which are non-zero, such that the divisor of f plus D is greater or equal to 0. We are going to say that it is effective. That's going to be the official name. Union 0 to make it a vector space. And what does it mean for divisor sum of NP, P to be effective? It just means that you want all the coefficient NP to be non-negative. Okay? So now we have a nice vector space, and it has indeed the condition we want to be finite. So this is going to be lemma 3.3.2 in the notes, which is that LD is a K bar vector space of finite dimension. All right. That's the first thing. Now, of course, we can say a bit more if D is a divisor defined over K. In that case, that's now lemma 3.3.3 in the note. One can show that L of D has a basis of K of functions over K. I'm just going to do the implication, because if you look at this lemma in the notes, it's a general lemma about the action of Galois on a vector space. So it doesn't say, the conclusion how it should be applied in this case. So let me just tell you. So implication of this lemma. So if you take D, so D, this is going to be a sum of NPP, and you say that D is defined over K, it's the case if and only if for all sigma inside the Galois group of K bar over K, you have that D sigma, which is by definition the sum of NP P sigma, is equal to D. But now, if F is inside L of D, then F sigma is going to be inside L of D sigma. Why? Simply, look at the poles and the divisor and look at the definition. If you switch everything by sigma, then, it is also switched. The equality that it is going to be effective is also just switched by sigma. But now, this is L of D. So what you proved is that you have a natural continuous action of gal K bar over K over L of D. And now you're in the condition of lemma 3.3.3, which says that in that case, it means that this k-bar vector space admits base over k, so there are functions which are going to be defined over k, which generate exactly this space. Okay, so already a small quiz for you proves that if degree of D is negative, then in L of D you have only 0. So it's not a very interesting space. Another property that is interesting is that, so if you take a divisor D, so let D a divisor, and G a function, then L of D is isomorphic to L of D plus div of G. So why is that true? I mean, simply because if you take F inside L of D, it means that div of F plus D is effective. And now, if I want to do an isomorphism, what I'm going to do? I mean, I'm going to now take, so div of Fg, so plus D. I mean, this is div of F plus div of G plus D. I mean, here there is a bit something to prove. I mean, that indeed the divisor of a product is the sum of the divisors. And so, but now, I mean, it means exactly that since div of D, F plus D, is positive, the divisor of Fg plus D, I mean, then this is going also to be positive. So the isomorphism is just going to be given by, to F, you're going to map it to F times G. Okay, and as a consequence that you can prove is that L of the divisor of a function, this is going to be isomorphic to L of nothing, and this is K bar. In particular, I mean, you see that in that case, I mean, it has dimension 1 as a K bar vector space, and well, as another quiz, describe more precisely what are the functions or what is the basis of L of div of F. Okay. So, do we have interesting divisors to try? Yes, we have seen in the previous lectures that, I mean, differentials give you an interesting divisor. I mean, so let kappa be the canonical divisor. I mean, it's only defined up to linear equivalence. So it means that it's only defined up to the divisor of a function. But we have seen that two Riemann-Roch spaces which differ by the divisor of a function are actually isomorphic. So we could take for kappa the divisor of any differential, non-zero differential. So I call it kappa the canonical divisor, but be careful that it's uniquely defined only up to linear equivalence. Okay, so now, I mean, I could consider L of kappa. So L of kappa, I mean, by definition, it's the function f in k bar of C, non-zero, such that the divisor of f plus kappa is positive, union 0. But now, I mean, kappa, as I said, it is the divisor of differential omega. So when I write this div of f plus div of omega, this is also the divisor of f omega. And I want this to be effective. So what I have just said is that L kappa is actually isomorphic to the space that is can be denoted, well, that's to a space of the function of the differential omega, which have no poles. So these are called the regular differentials. And one nice thing, I mean, this vector space has finite dimension. So this is now the definition we want. So we call the genus of C is the dimension of L of kappa. So finally, that's the invariant we are going to be interested in. Maybe I should have said also, like in general, another definition, if D is a divisor, we are going to denote L of D with a small l, the dimension of L of D with Matcal L. Okay. Maybe one example of computation of a dimension of Riemann Roch space. So let's take the following example. So for C, I'm going to take P1, and I'm going to take, for the divisor D, the sum of 3 points. So let's say 0, 1, and infinity. So when I'm looking at L of D, I'm looking at function, so rational fraction, or, well, let's say of quotient of x and z. So let me write it more like not identifying with the k of x directly, but k of p1 non-zero, such that the divisor of f plus 0 plus 1 plus infinity is positive. But now it means that this f, its divisor, I mean its poles, can only be at 0, 1, or infinity. So how am I going to write such an f? Remember that it's a quotient of two polynomials homogeneous in the variable x and z, let's say, of the same degree. So what I'm going to have in the denominator of f, so f belongs to L of D. If and only if I can write f as a fraction, and I'm going to write the poles. I mean, the poles, remember, they are in the denominator. So 0 has to be a pole. Okay. So it can be a pole. I mean, so x can be here. Then I have also 1, which can be a pole. So I have x minus z. And finally, infinity can be a pole. That means that it has a z here. Okay? And now the numerator can be any polynomial in x and z, homogeneous, so p homogeneous, of degree 3. So what is the dimension? Well, I mean, the dimension is the number of monomials inside an homogeneous polynomial of degree 3. And this is 4. So I find that L of D, in that case, is 4. Okay. In general, of course, if you're not over P1, then the computation of a dimension of Riemann Roch space could be much more complicated. Luckily, I mean, there is a very powerful theorem, which is really going to play a central role in all the theory. So this really big theorem, it's called Riemann Roch theorem. And honestly, when you look at it the first time, you say, well, and so what? Because it really looks like something that is not interesting, or at least not very powerful, but it is really powerful. So what it says that for any divisor D on a curve C, of course, the dimension of the Riemann row spaces associated to D can be computed as a degree of D minus, so G, where G is going to be the genus of C, plus 1, plus another contribution, which is the dimension of the Riemann row space of kappa, where kappa is our canonical divisor on the curve, minus D. Okay? So this is really a fundamental result, which is theorem 4.1.1 in the notes. And if you look at the notes, I mean, there is a long proof of this result. And it's long because, I mean, this part, the degree of D minus G plus 1, I mean, it's somehow fairly easy. I mean, if you just want to have an inequality. But to relate this, I mean, there is a kind of duality. You have to relate somehow the dimension of the Riemann row space is at D with the dimension of the Riemann row space at kappa minus D. And this duality is really important and somehow profound. And it relies, I mean, for like the classical proof we give inside the notes on a notion which is a residue theorem. So I invite you to look at this proof. Of course, there are plenty of other, some which are much quicker. If you know about cohomology, for instance, you can go much quicker with the proofs. But I mean, at least the proof we give inside these notes, I mean, it's really like, let's say, pedagogical and down to earth. But I'm not going to say anything more about the proof. I mean, I'm really going to be more interested in the consequences of this result. And as a first consequence, what I want to take for D kappa itself. So if you do this, then what do you find? You find that L of kappa should be the degree of kappa minus G plus 1 plus L of nothing. And we have seen that L of nothing is 1. So, and we have said that L of kappa is by definition G. So if I put everything together, this gives me that the degree of kappa should be 2G minus 2. And remember, we had done some computations, so the next quiz is easy. Just check that this agrees with what we did for genus 0 and 1. All right. Okay. Now, let's speak about this L of D, this dimension L of D. So, I mean, it measures how many functions you have inside the Riemann row space. If it's 0, then it's boring. So L of D equals 0 is really boring. I mean, what can you say if you have just 0 inside? So we are going to consider now the case where L of D is at least 1. But then it means that there exists a function such that div of f plus d is effective. And we have seen that, I mean, Riemann row spaces, they don't change so much if you look at the div of d or d plus div of f. So I can, and I will now, replace my d. I will just consider the d which are effective, which are of the form d greater or equal to 0. If I do this and I look at L of d, then inside L of d I have always at least the constants. Because the constant, I mean, they satisfy that the divisor of a constant, it's nothing, plus d, it is positive. So that's why, I mean, the dimension is greater or equal to 1. I mean, this is a one-dimensional subspace. And of course, if there are only the constants, then it's also a bit boring. Okay, I mean, what can you do with the constants? You don't do so much. So the trick now is, instead of looking at L of D, we are going to look at the projective space associated to L of D. And you can look at the dimension of this projective space. And the dimension of the projective space is 1 minus than the dimension of the vector space. And we are going to call this number R. So what does P of LD represent? It looks a bit like it is really abstract, but it is not. Because remember that two functions, f1 and f2, have the same divisor. So let me write it. Div of f1 is equal to div of f2 if and only if there exists an alpha in k bar non-zero such that alpha f1 is equal to f2. So what am I measuring by taking the projectivization? I mean, this space P of LD is actually the space of effective divisors, or the set of effective divisors linearly equivalent to D. And this is a very important concept, I mean, that is denoted by bar D, which is called the linear system associated to D. Okay. And among the divisor D, we are particularly interested now in the one, so definition, a D for which R is greater or equal to 1 is called special. Okay. No, sorry, that's not exactly the definition I want. A D, okay, because, well, we'll see later, but a D is special if what I want is L of kappa minus D, which also is called I of D for index, is positive. Sorry. I mean, we will see that, of course, I mean, it is a bit related with the value of R because of the Riemann-Roch formula, but I mean, this is really the definition. So let's see. Let's put a diagram to try to explain the relation between here D and here I'm going to put R. So it starts at 0. There is a special value which is 2g minus 2. So the degree of the canonical divisor. And for the degree of the canonical divisor, we have L of D equals G. So R is going to be G minus 1. So that's kappa, and that's G minus 1. Okay. If you look at the proof of what was the lemma 3.3.2, it doesn't only tell you that the dimension of the Riemann-Roch space associated to D is finite, it tells you also that it can't grow too fast. And actually, R can't grow faster than D. So what you have is that you have the diagonal here, okay, which ends so at a point here which is going to be 2g minus 2. And necessarily, the R is under this diagonal. Now, I mean, you can also look at the Riemann-Roch formula. I mean, if you look here up to G, you see that classically, I mean, if the divisor is not special, then I mean the dimension of, I mean, R is going to be 0. Okay, because simply if you look at what is L of D minus 1, I mean, you have the degree of D minus G. So already, even if you're smaller than G, you're not going to have a R which is positive unless L of kappa minus D is going to be positive. And unless then D is special. So non-special divisor. So non-special are here. And then they grow. Just because the degree grows. And you arrive at a point which is here just under it, right? Yeah. So it grows with a slope which is also 1 here. And then it means that your special divisors are going to be here. And I stop at 2g minus 2 because this is the degree of kappa. So if D has a degree which is bigger than kappa, a divisor is never going to be special. I mean, the L of a divisor which is of negative degree is necessarily 0. That's also something we said before. So this is the situation. But now, I mean, you could say, all right, can we do better? I mean, can we try to understand it better? And indeed, there are other kind of bounds. So the first one is called Clifford's theorem. And Clifford's theorem tells you that this is not the best you can do. You have another line which goes directly till here. And so your special divisors are here. So this is Clifford's theorem, which is given as an exercise 4.2. Okay, and you might say, oh, nice, but is that the end of the story? And still not. So let's see, we have more colors. Blue. There is actually another curve this time, which is like this, and tells you that no, I mean the special divisor, they are really here. So this curve is the Brill-Nutter curve. And it has a complicated equation, so let me take the paper. So it's G minus R plus 1 times G minus D plus R equals 0. And this, I mean, there is no proof in the course. I mean, I'm telling it to you now, I mean, for like completeness, let's say, but this is really much more involved as a result already. That goes much behind the material of the course. What I would encourage you to do as a quiz is just numerical computation. Check what it says. I mean, check where special divisor can be. For G, 3, 4, and 5.